Well, hi, and thank you for joining me here in my shop. Today is March 25th, and what I'm going to be doing is taking some voltage tests to make sure the key tube voltages are correct now. And wait a minute, there's still 2 more capacitors to do. That's okay, I'm going to do those voltage tests anyway. I sort of forgot I still have capacitors to change out, but not this one. Made an interesting observation in this radio. I'm going to show it to you. And it can be your observation too. I don't think this is anything unusual or whatever, but it's worth taking note. Different radios do things differently. This one's using the Loctol style tubes. The tube socket is a little different. It has a steel part in here that snap locks the pin that comes down. Every one of them has one of these. You can see it here. See it here. I'm guessing this all attaches metallically to this base, but I'm not sure of that. I don't really know where it's going. But there's a terminal here and a black wire, and I follow the black wire, it comes to this one. The black wire continues, it comes to this one, and continues and comes over to this one. If we go back here, there's a black wire, comes down, comes from this one, this tube right there, the same spot again, the center post on the tube, and the black wire comes over to this terminal. This terminal on the terminal strip here is the terminal that has the rivet that's riveting it down to the chassis. So this terminal is actually a chassis terminal. This one's not. Whenever you look at these strips, you have to look and see which one is the one that's riveted down. In some radios there'll be no connection there because I don't want to connect there. So this is the connection point to the chassis, and what they've done is they've connected all these tube sockets, I guess, maybe I can say that, also to the chassis electrically to make sure they're not independent floating pieces of metal, because they become antennas and then they can radiate back into the radio. What might they radiate? All kinds of radio signals themselves can get radiated around and end up looping around and coming through again, and so that's feedback or oscillation going on. Not good to have just floating pieces of metal around here, so they're grounding them, or another term that could be used, not usually used with radios, but it's used with electrical distribution, would be bonding. You bond, the rule is to bond all the non-current carrying pieces of metal together and tie them to the power system neutral, or in this case to the chassis. So that's just something worth observing. And you see this coil here, one lead is also tied right to the chassis. Well, this has got to be the antenna coil, I would have to guess. Now another thing I was trying to sort out here is there's 2 places here for plugging something in on the service panel that's called the accessory. What accessory? What kind of accessory? I mean, what is it? And by looking at the wires under here, I kind of believe it's for an external speaker, which is kind of weird. This blue wire, which appears to be coming to this terminal, this blue wire comes down here, goes through the chassis, shows up on top, and comes up to the speaker. So didn't look any further than that, but that looks like this is like external speaker. That's really weird on a little radio like this. So I'm not sure what these are yet. The last thing is this blue wire coming out here, which is then screwed down to the chassis. It's on the outside of the radio at the back where a owner or user could access it. If you wanted to use an external antenna with this, for some reason you wanted to put a long wire on it or something, you would undo this, pull this off so the blue wire is no longer tied to the chassis. Hook your antenna up to this wire. This is the antenna wire. But when relying on the loop antenna here in the radio, this wire must be grounded to the chassis like this. That's what's going on there. Got that out of the service manual. Didn't think that up on my own. Okay, voltage tests. Even though I haven't done all the capacitors yet. So I wouldn't imagine any like these capacitors can be causing a DC voltage problem. It would be a little far-fetched. It's possible, but it's not very likely. So the test I'm going to do is probably valid before and after these capacitors are changed out. So I want to put this on the B minus and make sure the radio is not plugged in. That's the best ways. Not rely on switches, but okay, we're going to go on to B minus. I can catch that right here. That's on the minus of my meter lead, and then we're going to be reading voltages. So we're on DC, positive, and the voltages are going to be around 100 volts. So I'll put it on the 100 volt scale right now. We're not looking for precision in these measurements. We're looking to make sure there isn't a gross problem like a missing voltage or something more aggressive like that. Let's take a look at the schematic here. So unfortunately the schematic spread over 2 pages on my screen here, so we have to flip back and forth. But here's the voltages I'm after. See, 92, 40, 92, 92, there's a lot of 92s in here, 40, and we go down to the next page, 92, 45, 96. Well, they got extra 4 volts there. Wow. So often the way these radios are built, the power supply has more than one takeoff, if you like. And it looks like that's the case here. It looks like there's something coming off here. Look, there's a voltage reading right there. And then there's something coming off here. So this is a filter filtering out the hum that's coming from the rectifier and the pulsing AC that's been rectified here. Comes in here and the pulsing is reduced greatly. Still pulsing a bit. Come through here and now it's smooth like baby's feet. So the thing is, you can afford to have a little bit of hum as long as a percentage it's very low relative to the signal that you're listening to. They won't hear the hum because the signal's too loud. So this is a slightly hummy power supply voltage here, 105. What do they do with it? They send it up and they operate the output tube with it. So a slightly hummy voltage here, but so slight you can't hear the hum. They don't need to over filter it. The other thing is, by taking off here, they get a little extra voltage just for the output tube. The output tube is the hard working tube that's pushing the speaker cone around, and it needs all the voltage it can get. These transformerless tubes are low voltage radios. They can't produce all that much. They can't produce 200 or 300 volts. You need a transformer for that. So the best they can do is about 120. Look, here's 116 here. But they don't do anything with this voltage. They don't run it into the radio. This is terribly hummy here. This is really bad. But by the time you get out here in the filter, you've now gone across 3 capacitors. I put big ones in here too. So by the time you get here, the hum level is extraordinarily low. So what do you do with it? You take this really refined DC humless voltage, whoops, and okay, it's on this wire here. That's this one. You feed it up to the earlier tubes. Whoops, this is going to the screen of the output tube. We won't worry about that. But you'll see that here it comes, the beautiful DC plate here, and a lovely DC all the way down here, and it's being applied through this coil to this plate. So all these tubes earlier in the radio have really nicely filtered DC, but the output tube, not so much. Why? Well, if you let this hummy voltage drive these earlier tubes, the small hum will get amplified and you're going to hear it. So you need even better filtered power for the earlier tubes than the output tube in particular. So they suffer the loss of voltage here to get a better filtering, a little bit lower voltage, and run the signal tubes earlier in the radio using this, highly filtered, slightly less filtered, going to the output tube. That's what's going on there. Okay, so you see how the A, D, B, now we know what these are. These are test points for voltage readings recommended in the service manual. But I'm just gonna go right on the plate here and the grid and whatnot. Not the grid, plate and the screen. The 2 things that carry a high voltage. Let's look at this tube here. You have the cathode, which is emitting the electrons, which is running near the chassis potential or near 0 or near B minus voltage. It might be elevated by a cathode resistor to provide bias, but maybe not. Then you have the next grid, the one closest to the cathode. This is the driven grid, the signal grid, the grid that's got stuff on it from earlier stages of the radio. And this is the one that's going to affect the current flow through the tube. And you could leave it at that. There are tubes that, like this one, it's just got a grid. It's got nothing else. But in this case, it's got two more elements in here. Now, one of these elements is right up close to the plate. This element is called a suppressor grid. It's tied right to the B minus. Sometimes internally it's tied right to the cathode. And this thing is intended to reflect back electrons which have bounced off the plate due to having too much speed, too much energy. They come through the tube, they strike the plate, they themselves bounce away, or they knock other electrons off. Those electrons come floating out here. They can get captured by the screen. You have a heavy screen current. And the thing is, those electrons no longer continue this path, so they're lost to the radio. They're not of any good. They're wandering in some other circuit, not affecting the speaker at all. So you put in this suppressor grid here. I don't want to explain tubes in detail, but just a little bit. And then this one, this is why I want to explain it. This guy in the middle, what is he doing there? So this is the blinder. This guy makes this part of the tube kind of unaware that this part of the tube exists. I know that sounds kind of strange, but by doing that, it reduces the tube capacitance. A vacuum tube is a big capacitor, right? A plate, electrode, something in between. Well, nothing actually, a vacuum in between. That's a capacitor. It's a small capacitor, but it's in a critical position. It's tying the plate to the grid. So if the capacitance is high enough, you actually get feedback right through the tube. The grid can see and feel the effect of the plate, and vice versa, of course. But you put a screen in here, and the grid loses sight of the plate, and the capacitance in that case becomes very, very low and not a problem. Screen grid. That's why they call it a screen grid. It's screening the plate from the signal grid. But it's not just in there, it's run at a voltage similar to the plate voltage, often just a little bit lower. In this case 40, a fair bit lower. Once in a while it's higher, but not normally. Normally it's lower. And this, in the end, acts a little like a plate in itself. It draws current from the current stream, so it robs a bit of current. And that current is kind of lost, it's not used for anything, signal current. So there's that deal. And so okay, that's enough explanation about tubes. I really don't like I have to do a special video just explaining tubes, because I'm really, these diagrams are very misleading in how a tube actually operates. This gives you some impression of what's going on. It's really much more complicated than what these suggest. But the model that this suggests is suitable for analyzing radios and stuff like that. But if you really want to know what's going on in a tube, it's a lot more than what is commonly understood. So, okay, enough of that talk. Now, so consequently, there's an important voltage on the screen, and that's why I want to measure it. So any tube that has a screen, you should find a plate voltage and a screen voltage. Two high voltages. Let me go up here. Look at this guy. Oh my gosh, what's going on in there? So this is a very special tube. We'll start with the screens. You see how these are connected together? These two? These are two screen elements in the tube. This one's doing the job I just told you about. This is the signal grid here in the middle of everything. And down here is a grid for signaling for the local oscillator. And I'm not going to explain all this right now. And there's an extra grid in here. I don't know what's this doing here. Wait a minute, there's too many grids here. 1, 2, 3, 4, 5, 6 grids. Huh? Wait a minute. One. My mouse sticks sometimes. 1, 2, 3, 4, 5, 6. You can see the suppressor grid in this tube is connected directly to the cathode. Well, there's something a little unusual going on here. This is a tube I'm not that familiar with. 7A8. Is it really has that many? Normally there's 5 elements. What are you doing with an extra one? What do you do with it? Must have caused the engineers quite a bit of concern. Well, okay, I won't sweat over it. Look at all these voltages now. We've got 92 here, 40 there, 92 here. It's reporting 2.3 volts on this line. This might be very difficult to actually read because this is the oscillator grid, and when you go to read it, you can shut the oscillator down just by attaching your meter to it, and then the voltage disappears. Anyway, we won't worry about that. I'm really after these higher voltages here. Okay, 3 on this tube. Wow, I wasn't even going to look at it. I'm glad I did, because it's very surprising. Extra grid. What would that be? That would be a sextode, as opposed to a pentode, as opposed to a triode. Sextode. That doesn't sound right. It doesn't sound like something you should say, actually. Okay, let's get these voltage readings going here. Okay, I think we're all set here. A little bit of a practice now. I'm going to start with the power supply, the 3 capacitors. And it's going to be these 3 red leads, but I don't know which one's which. So I'm just going to test them, and we'll just compare against the chart there, which shows 116, 105, and 92. So that's what we're looking for, those 3 voltages. Okay, I'll turn this guy on. There we go. Just making sure everything's normal again. Looks good. Okay, full voltage for sure. So this test, a mistake somebody could make is to read the voltage to the chassis. That's not the right way to do it. And that's why I have this yellow clip lead here. That's actually attaching to the meter negative. So you see me waving the positive around. There we are. Okay, radio's working, but we don't need to listen to it. Maybe just a wee bit in case something happens. Okay, so here we go. Now I'm on the 100 volt scale here. So one of these voltages is going to go right over. Let's see if we can find that. That one's just under 100 according to that meter. That one's just over. This last one is over a little further. So I see 3 different voltages here. I'll put this way, let's actually read them. Okay, 300 volt scale, so that's 125 on there. 125. And this reading is 110 or 12. And this one is just under 100. I think it's perfectly normal. The readings that were taken that are shown on this chart were probably done not with a expensive meter. This is actually a very high quality meter. This is a transistorized amplified meter. And what that does is it means when you touch the probe into the circuit, it doesn't draw very much current at all, just a tiny amount. It won't disturb many circuits in a radio like this, so you can read around with it. But these kinds of meters were not common back in the day. What was much more common back in the day would be a meter like one I'm looking for right now to flash at you. And where'd it go? I don't see it. Drat. These meters are what's in this thing? Let's look at this. What is this? What is this? I'm not even sure what I got here. Looks cool. Let's see. Yeah. So this is much more the kind of meter that would be used in a shop back in the 1940s. These things draw power to operate. This one uses transistors to develop the power to move the pointer. It doesn't need power from the circuit. This one needs power from the circuit. The result is, let's do it. The result is the reading is going to be lower. Now I don't know if I've ever actually used this meter, so you know, who knows what to say about what the result might be. Okay, so we look at the scale here, ohms, DC volts. Nice 250 volt scale there. So what we're doing now is we're comparing a reading taken with an older meter and a reading taken with a younger. And they're all both old. This one's not nearly as old as this other one here. Put it like this. What a cool, yeah. See, really cool arrangement of meters there. Sit there, would you? And you can't read them because I got just too much light in my shop here. You'll have to trust me. Okay, I'm going to clip this negative lead in here. There we are. Okay, now what happened to the other red pointer? Oh, son of a gun, it's buried under here. So we need to go into the radio a little bit. We need to look at the lower voltage. This isn't even a good spot to do this. We should try just pick off a voltage out here somewhere. Anybody got a voltage? Who's got a voltage? This is what I have to do anyway in the end. There we are. We got a voltage here. Okay, so with that meter, dumb arrangement. Put it on the 100 volt scale. I was touching this, I think. Yeah, so we've got on the 100 volt scale, that's 80 volts according to this meter. Now you might argue, well, how do you know this meter's accurate? I have checked it, it's pretty accurate. Now we'll switch meters, and for the first time we'll try this guy. Maybe it's going to blow up, I don't know. This is not handy, this container it's in here. There. Okay, so we're on the 250 volt scale. Last meter read 100, so it should come up right around in here. Here we go. What was it I was touching? This thing. So this one reads I'd say it's just under 125. 125. It's reading higher. It just blows it right out of the water what I was going to say. We need another meter. You know the story about the guy with two watches, eh? The guy with two watches never knows what time it is, and that's what's happening here. We're not going to know what voltage it is. So this is a highly reliable meter, I'm pretty sure. I think we can trust this one. I do have another one that I know is quite reliable. These digital ones, I'm sure, are super reliable, super accurate. High input impedance won't draw the voltage down. Should show the same as this. Not 125. Let's find out. Okay, so I got to put this on the negative. Put the negative on the negative. Can I shove another one in? Okay, we're just going to go with the 1 meter connected. This one. What's he doing? Does anybody know what he's doing? What are you doing, man? Here we go. And the number is 81. 81 volts. Do you want to believe it? I think this is the meter I would trust the most for accuracy. 81 volts. The other one read 125. It makes the story I was going to tell completely ridiculous. But I will tell it anyway because it is the official story. So the more a meter draws off the circuit, the lower it's going to read because the circuit voltage itself will collapse as you're making the measurement. So this guy might read 100, this guy might read 80, but the voltage is the same inside. I mean, the radio is operating the same inside. The voltage isn't. You actually are pulling it down, but that aside. Only this meter ended up reading higher. I'm going to do it one more time because I doubt myself. Okay, here we go. I'm going to hold 2 probes in at the same time here, not get a shock. That's the plan. Ooh. Yeah, I got the radio on a rotating surface. That's good too. And I got it tilted on its side, it's ready to fall over. Quickly, somebody take that reading. Oh, it's even higher. That's one. That'd be 125, 130, 135. Don't use this meter. That's what that says. Kind of surprising. It measures high. Wouldn't you expect an old meter as it gets older, it's going to measure lower and lower? It's like saying an old guy runs faster and farther. It doesn't really make sense. Okay, so that was a total, this is a live channel here, and it demos, explode right in my face. What about this meter? Yeah, now here's a real, oh no, this one doesn't even have a scale on it, does it? Does it have a scale? DC volts, 150 volts. Ooh, you want to try it? No, I'm not even going to try this. This is too chintzy. That's a battery tester at most. I do have another really nice one I'd love to try now, but too late. Time's up. We're moving on. I'm going to take this clip lead out of it. No, I'm going to leave it there. I'm going to leave it there because we're carrying on. Which meter do you trust now? Well, because we're not really making precise measurements here, we're just looking, is it there, is it not, kind of thing. Okay, so we did the power supply, found the 3 varying voltages, apparently in the right pattern. Let's just go and take a look at the output tube. So we have 2 pins to test, pin 2, pin 3, at 96 and 92. 96 on the plate, 92 on the screen. Right? The screen is a decapacitor for the tube. Reduces the tube's capacitance. Or what acts as an internal short, especially at high frequency like RF frequencies. 2 and 3. So there's the output tube here. Pins, just making sure, pins 2 and 3. So this would be pin 2. On the 100 volt scale, we're reading 84 and 3. We're reading, okay, so let's make it more accurate. That's 80 on this meter. And this is 83. So we're a little higher on pin 2. And we should be higher on pin 2. The fact that it's just a touch low really doesn't. As long as the relative voltages are proper. This is higher than this by a little bit. That's good. We're done. Next tube, 45 on pin 2. 45 volts on pin number 2. And this is on this tube down here. Pin number 2. So we're looking at 1. This is pin 2. 45 volts. So we're on the 100 volt scale. You can see straight up would be 50. That reads 44 volts, 42 volts, something like that. That's the only voltage on that tube because it only has a single grid inside. Okay, my ears started ringing. I don't know, is it my ear ringing or is there something frying up and burning in my shop again? Okay, we'll go to the next tube back, 92 volts, and this one, 92 volts, pin 2. Let's start with this one. Pin 2 and pin 3 should have voltages on them, 92 and 40. Pin 2 and pin 3 on the, what would be, I think, this tube right here. Pin 2, so that's 1, this is pin 2. We got pretty high voltage there, 80, and pin 3. About half it, around 30. 32, 33, 80. 30 and 80. What do we get? I want to look again. It's supposed to be 90 and 40. So I think that's probably okay. Again, it's a little low, but the ratio is right. I could correct it by just cranking up the supply voltage. Right now we're running at 114 volts. You know, if I made it 118, that might come out normal there. But the main point again is voltages are there. And now we got this complicated tube here to do with pin 2, 5, and 3. 2, 5, and 3. 2, 2. So if we did them in voltage order, it would be 2, 3, and then 5 is low. 2 and 3 same, 5 low. 2, 3 same, 5 low. Here's the tube. 2 and 3 the same. 2 is 80. 3 is 80. And then 5. And about, so that's about 35 volts there, a little under 35. So what this says is the tubes all have good voltages on high voltages on the elements that need them. And that suggests that the resistors in here are okay. Typically these voltages get thrown off by one of two things. Either a resistor's gone way off, or you have a badly shorted capacitor pulling something down somewhere. Okay, now I could choose to leave everything just as it is now. The radio is operating. Or we can go further and change a couple more capacitors. So we have one here that all the audio is going through. And this one, I think if it's leaky, this one might present a bit of a problem. So we're going to take a look at this one. This is coming off the volume control. The slider part of the volume control, you're selecting how much volume to put through the capacitor onto the preamp and then to the output tube. So let's take a look at this capacitor on the schematic. Well, I got the schematic on the screen. So that capacitor is on the volume control. So let's find the volume control. Here it is, right here. And this is the capacitor we're talking about, right here. And see, it comes up here. Now look, if you come down this way, you get a gigantic resistor. So no charge is going to come down this way, or very, very little charge will make it out this way. And you go this way, it's just a grid stuck in a vacuum. So there's no current flow this way. So what can happen here is, and go all the way back to here, there's a DC voltage here. It's generated by these diodes, one of these in particular. That DC voltage can go all the way through and stop here. You can't get across this capacitor. If it did, it would start throwing the bias off on this tube. And we're not talking about a lot of voltage here, but 5-10 volts over here. But that's possible. If this guy were really leaky, the leak would get through, the voltage would get through, the charge over here can't find its way out through this large, or finds its way out very slowly through this large resistor. And I just realized somebody's coming to my house to pick up a radio, and I better go check that out right now. So the point is, a small leak here cause a voltage to build here. Now the whole thing about talking about meters. Oh, I gotta go. Oh, I gotta run. Okay. So one of the radios I worked on is on its way home now. Okay, so the capacitor we're talking about was this guy here. Now, I think I was going to try to read this voltage, and I was about to explain that if you put a voltmeter here, you're liable to bleed off any charge that's built up in this little bit of stuff here, and the voltmeter will show you a lower voltage than what is there when the voltmeter is not connected. This is probably one of the most sensitive spots right here for this problem in the radio. But let's give it a go. So it's grid number 3. And what are we expecting? I don't know what to say about this. Let's just see what happens. There shouldn't be any, I know what to expect. 0 should be here. Any leak through here should be, hopefully, is so small that the charge bleeds out through this big resistor, never builds up a voltage or a pressure in here. That's the way to look at it. Okay, so we're going to put the voltmeter on the detector tube pin 3. Okay, voltmeter onto the detector tube pin number 3. Detector tube is here. Pin 3 would be 1, 2, 3. So there's the, I could have found it this way. There's the capacitor feeding the pin. I could have gone this way. There's the resistor that's bleeding out any charge that might build up. We touch it, watch the meter very carefully now. We're looking for really no voltage. So here we go. So I got this on the 3-volt scale. What is going to happen? Touch it and watch the meter. It's dummy. It's a negative voltage. Let's try it again. Yes, it would be a negative voltage. So there is a voltage there. Now let's look at the other side of this capacitor. Well, isn't that curious? Now let me change the volume control here. Yeah, give me a clip. This isn't dangerous. It's just it's hard to maintain a connection there. What happened? Yeah, that's right. There's next to nothing there. See it? See it dip and then come back? Now. There's a distortion. So the volume control is a variable resistor, and it's allowing through more and more of that voltage. Wait a minute, yeah, that's right, because this is set to negative now. So an upscale reading is a negative voltage coming from the detector, making it through. Well, it's not making it through. We don't know. Move this now. The other side of the capacitor. Now, hooking up the meter here might disturb the sound. It does. It does. A bit of a hum in there. Now do this. Only at the highest voltage, highest volumes, does a bit of the current. Is the elite current sufficient to push the voltage up on the grid? Okay, take this off. Try that again. So with the clip lead on and the meter connected, there was distortion in the sound. I think I was probably disturbing the circuit, and I probably got false readings there. I'm going to change this capacitor anyway. Let me just do one more. Do the same thing one more time. The negative voltage sitting there. You want a negative voltage there, and the negative voltage will actually develop on its own from something called grid biasing, which you could look up if you want to read more about it. But the grids will, if the circuit is correct, the grid will make itself negative on its own. Okay, so far everything's good. We'll change that capacitor next and poke around some more. Okay, new capacitor is in. This little green guy here. Let's give the radio another try. See if there's any difference in its operation. So I noticed some distortion at high volumes, but really was exacerbated by the meter I had connected. Let's see what happens here. Lots of volume. I guess that's a lot more. Yeah, that's a lot more because I was turning it up quite full. Excellent, excellent. That seems to go very loud with no distortion. Let's see what we got here for voltages now. Ooh. It didn't do that last time, did it? So, a similar reading on the other side. So what's going on now is I'm bleeding off. No, I'm not. No, I'm not. Nothing there. And the grid, negative bias of about a 3/4 of a volt with it. Oh, it's interesting. It didn't hum before. Don't know why that is. Maybe I had the volume down when I was doing it. That might be why. Okay, so that didn't hurt. It seems to have helped a lot with the volume, though. Let's test the capacitor. See what we got rid of there. Turn that down. Okay, and the capacitor in question is this one. I left just enough wire here. Okay. Now, watching the eye, 50 volts. And it just barely opens, just barely. So she's a leaky guy, that's for sure, as you know, relative to other capacitors. How leaky? It's not a quantitative test. But I think in that position, you're much better off with a fresh capacitor with no propensity to leak a charge across it. So where we're at now we got a loud radio, appears to be receiving with a boost of an antenna. I still have 3 original capacitors. They all appear to be in good shape. This one I am not going to change because it has a coil built into it somewhere. We can't even see it, but somewhere there's a coil of wire related to this. I would be remiss to not replace these, even though they're probably in good shape. Good enough shape. What are they doing? Why don't we try to find out what this guy's doing? So he is connected to, looks like ground here, from what I can remember of the wiring, and over to here. I've got this voltmeter here. Why don't I just check what kind of voltage is on here? Now I need this set to positive. I got this set to 3 volts. Holy smokes! Lucky I didn't see something. Oh yeah, that's so shaky. So that's about 30 volts on this capacitor. I think this other side is ground. This guy, it looks like, I'm not sure, this side is grounded and this side, no voltage showing up. So what's he doing? He's got no voltage. What's he doing there? Okay, so this one is tied. Let me look at this tube. This is the 788 tube. We count the pins. 1, 2, 3, 4, 5. Pin 5 has this big capacitor on it. Let's look at the schematic. Oh, I got the schematic up here. Pin 5 of the first tube is going to be right here. Pin 5 is this one. 0.05. Okay, follow this up. Nothing there. Resistor here. That's got to be it. 0.05. That's too big to be a 0.05, isn't it? And where? So one and the other end is going to be minus here. This is how I found it. That's what it must be. C302 0.05. Okay, it's a great big capacitor. So what's it doing? So you see, it's on these screen circuits I was talking about earlier, whose job it is to fool the grid into thinking there's no plate in the tube, and it's got voltage on it, and because it's positive, it draws current. So there's a current flow on this guy. Can't be much. Look at that. Can't be much. That's probably why the voltage is so low, 40 volts, because of that great big resistor there. 40 volts, that's roughly what I read across it too, isn't it? I did. So this has to be the capacitor, 0.05. If this isn't working well, you could get oscillations. You can get wild oscillations, so your radio's screaming funny tones and different things. I'm not sure what else it could do. Maybe just quiet down the radio if it's not working well. It's in a high current circuit, so a little bit of leak through it doesn't mean much. In this case, there's lots of current available, lots of charge available, so unless this thing was ready to catch fire, which I doubt it. So 0.05, surprisingly small, I think. 0.05. Going to repeat that again. So I started removing this capacitor, and I noticed something I'd like to show you, and that is I desoldered it here, and it just came right off the top. So this does not look like factory work. Factory work doesn't pop off like that. This looks like something I would do in putting a replacement in and trying to get this onto the terminal. I think this is a replaced capacitor. This side's very similar. In fact, it looks like it's just barely soldered in. It looks like it's just tacked on top. No, it is twisted around. But there, but not much to it. So I think this might be a replacement. Oh, quickly. Making the big mistake here. I've made the mistake. I don't know where this came from. Phooey. How do you like that? I should have. Yeah. Okay, I'll have to sort that out by looking at the video now, because I made a boo-boo there. Can't be sure of what I'm doing anymore. Okay, let's test this. Let's test this guy. Let's test him. Oh, I turned off the tester. We'll just turn it back on here. You know, it's a wonderful thing fixing these radios up for other people. When they often when they call me, they have tremendous doubts that their radio could ever work again because it's been dead for 35 years, sitting somewhere, and it's just kind of a lark. They're calling me up, and then eventually they're going home with a working radio, and they are so excited about that. You know, I guess so. Eh? Decades of looking at a dead radio, and then suddenly it's working. I can see why that would be cool. Okay, here we go. Here we go. Oh, it's nowhere near opening. So it raises an interesting question now. How well can something like this work in the radio? Is it can still do its job, or is it not doing its job? Or where'd it come from anyway? Where'd that come from? Came out of here. See, some of those tied to two of those terminals. Pick two, solder it in, see what happens. I have on occasion operated radios with these capacitors taken right out of them, but I think I would do that with my own radio to experiment, not with somebody else's. But the one case where I've done that, where I've left a capacitor, a big one, out like this, made no difference in the operation of the radio. I was floored. Okay, I'm going to put another 0.05 in there. Okay, on to this one now. That's the replacement there for the last one. This guy, I'm gonna guess this is I don't have to guess. This is a ground terminal here, and the other, ooh, look where it goes. It goes over here to where I put in the across the line capacitor. What? Huh? Okay, let's see if we can sort out. So one side is the cross-the-line capacitor, the part that's connected not to the switch. And this side, I measured this going to, I think I did. Where'd it go? Right there. Oh yeah, right with this negative wire is connected. Am I saying that right? Maybe I'm not. I think I'm not. Let's just put the close-up camera to work here. What's going on right in here? Another really busy spot. So this is the terminal that the capacitor is hooked up to, right? Is it not? Yeah. And then the black wire is on the terminal beside it. So that's not necessarily a grounded terminal. It's got a bunch of white wires hooked up to it. What are they for? Oh, it's going over to an IF transformer. And this other one going somewhere. Heading topside. Huh. Okay, and I'm not gonna. This is it coming up here to the SE antenna wire. What? Going all the way to here. Okay, not making a lot of sense to me. I'm probably getting something wrong. Name of the game is to replace this capacitor anyway, and it's a, how much is this one? How much? Autofocus, gotta love it. .05. Great big thing like that. 0.05. Okay, let's take them out. I've left some wire here, so I won't get lost. That, same thing here. Quickly to the tester. This looks really good. This one looks really good. I think I'm an example that, good looks really don't matter. Okay, here we go. And she won't open at all. Look at that. What was this guy doing? What was this guy doing? You have to imagine a larger physical capacitor it's going to be easier for it to leak more current through it simply because there's larger surface areas involved. 600 volt. Part number C209. What? They actually have the part numbers written on these? Where'd the other one go that I took out? What did I do with it? C207. Well, the whole story about this being, well, actually that's not the same capacitor. Here it is, here it is. So this was the audio capacitor coming out of there. So they don't seem to have a number written on it. So like just the value of 0.05. But not. This actually has a part number related to the schematic. Part number C209. Never seen that before. Okay, and it's definitely a 0.05. So I'm gonna find the 0.05. I'm out of 0.05 capacitors, frankly. So probably something a little bigger is gonna go in there. Where's this capacitor in there? Yeah, I'm not gonna worry about it. Getting too late in the morning here. I gotta find a replacement. You know how it goes in life when you usually figure out how to do things when just about the time you finish. You realize, oh, I should have done this or that. So looking at the schematic here, look. Section 2, audio circuits. And all the parts are numbered with the 200. The 200 parts are inside this box. If we go over here, which we can't, we can go down. We go up, we go up. Go up here, other part of the schematic, and we see section 4, RF and converter circuits, and all the components are numbered with a 400. 400. 400. So I'm holding part number 209. So we would look in section 2, which we were just looking at. Section 2. Find 209 in section 2. How far down does the box go? So it's just here. Not many capacitors. So you're 200, 203, 202. My mouse is hanging up. 201. 201. Where's 4, 5, 6, 7, 8, and 9? They aren't on here. Okay, so if we look down parts list, and now that'll reveal what's going on. So here's section 2, audio circuits. 200, 201, 202, 203. Where's 204, 5, 6, 7, 8, and 209? They don't exist. So what is marked on this capacitor? Because it's kind of weird that it has a number like that. So I think it's further evidence that these are actually replacements and they came out of another radio. I don't know. I like to make stories up about these things and try to explain them to myself. You know, as human beings, we're a lot more comfortable when we think we know what's going on. We don't have to actually know what's going on. You just have to think you know what's going on, and then you're a lot more comfortable. I think I mentioned that I'm out of 0.05 capacitors, so I've picked two capacitors here, a 0.04 and a 0.01. Together they're 0.05. And you can see it right there, 48 nanofarads, which is 0.05. Okay, so I have to put two in parallel. And these are lower voltage capacitors, but it doesn't matter because the service is very low voltage. Just, you know, a big voltage for these would be 20 volts. And these are 100 volt capacitors. And they're going to go right in here. So I'm going to get rid of this. And get rid of this. Quick check to make sure the radio's shut off. Okay, that first solder didn't really take. Okay, they look like they're in. There you go. I don't normally put that on video, but I did in this case. Let's take this off here. Why would we do that? I don't know. I don't know. Okay, I'm going to try the radio one more time. That's it for wax capacitors. They are all out. Okay, volume is down. Plug is in. Power's on. How are you going to work this time, radio? So we still have the antenna augmentation coil sitting here, this white one. So it's still getting a boost. Does it need it? I don't know yet. The next thing on the hit parade is to do an alignment, and that's where we might increase the performance of the radio quite dramatically. If it's still weak on its own, well, it's picking up stations, so. Okay, radio's working. So any performance issue that is in it now is either something I haven't discovered, which I don't think there is such a thing. I've done the voltage tests and stuff like that. So probably the low performance is due to bad alignment. I think we checked the IF already on this radio. I can't remember. Why would I have done that already? I don't know. So tomorrow we will do alignment on this radio, and we'll go through it and make sure it's tuned up for maximum performance, and then we'll be able to judge, was this a good radio or not? It's a lovely looking radio, that's for sure. Well, thanks a lot for watching, and before I forget to do that, I'll see you on the next video. Bye bye.